Today we're going to talk about the very special case, very important case of free fall, which is just a subset of constant acceleration, but has lots of interesting implications. In the early days of physics, Galileo noticed and experimentally verified something very strange. Anything you drop seems to fall with not only a constant acceleration, but with the same constant acceleration, no matter how big the object is. So we see over here on the side, what we're looking at is a feather and an apple dropped out of a chamber in a vacuum, which is obviously not something you can see from the picture, and we see that for the distance that the feather falls, at every moment the apple is at the same height. So they are falling, hitting the same positions at the same times, meaning they must have the same velocity throughout, which means they must have the same acceleration throughout. It's not as obvious from here, but these distances are obeying that this acceleration is not only the same throughout, but it's a constant value. And I want to stress here that there's two ways we can say that things have a constant acceleration. One, their acceleration doesn't change, duh. But two, they have the same constant acceleration, and that's the case for free fall cases. Here we have the cameras flashing at constant rate, so delta t is the same for every image. The feather falls a greater and greater distance, which indicates accelerating, and the apple stays even with the feather, so it must have the same acceleration. There are a few caveats. It really only works well if we can neglect air resistance and other influences. And it really only works over so-called short distances, so-called near the surface of the Earth. The little quotes here to say these are weasel words. These are things that we need to clarify. But the Earth's radius is 6.4 million meters. Near can be several kilometers of height. That this is still pretty good up to as high as human beings had ever gone before there were airplanes. So fair enough to say, at least by the surface of the Earth, this is a true thing. Under these circumstances, any object falls with a constant acceleration, and we generally symbolize the magnitude of this acceleration with the letter small g. For an object near the surface of the Earth, it has been established experimentally that g is the quantity 9.8 meters per second squared, meaning that something falling near the surface of the Earth gains 9.8 meters per second of speed every second that it falls. And remember that means it's gaining a pretty hefty amount of velocity for every second. Please note that g is defined as a positive constant. There has been some disagreement on this in the physics world up until, I don't know, the 70s, and there has been disagreement in the textbook world even later, and there are still middle school and early high school textbooks that still get this wrong, and I'm not usually one to say this, but they're just wrong. The universal agreement is that g is a positive constant 9.8 meters per second squared. Since we usually say that upward is plus, then the acceleration, which is downward, we would say the acceleration is g downward with the minus sign. But be careful, right? So the acceleration might be minus 9.8 meters per second squared, but g is not minus 9.8 meters per second squared. The acceleration is minus g. The value of g varies a little bit from place to place. I've been cheating a little bit here. This is how they do things like find gas and oil deposits by looking for small variations in the acceleration due to free fall, but we're going to use 9.8 meters per second squared and ignore that variation for this class. Objects moving only under the influence of the Earth's gravity are said to be in free fall. Despite the verbiage, objects in free fall could be moving upward. Yeah, it's a pretty silly term. It kind of comes from connection in German, I believe, but don't worry about it. All that really matters is that they are free. That is, they're not affected by anything but the local gravity. It's important to recognize that the Earth doesn't really get a privileged status. That if you were near some other large astronomical object, then you would have constant acceleration, but the value would be different. So if you go up to the moon, the acceleration of gravity on the moon is something we would often write as g sub moon. Also sometimes g sub and a little picture of the moon. And that's about 1.6 meters per second squared. Things weigh about they fall about 1/6 as fast on the moon as they do on Earth. On Mars, it's about 40%. At the edge of Jupiter, it's about 2.5. So it's like 25 meters per second square. So know the 9.8 meter per second value, but realize that it's a local thing based on Earth. Some other ways of representing that. If we have an object dropped from rest, the velocity vectors point down, and they get longer, which makes sense. All right, and that acceleration is g, downward. So if we were to graph it, the velocity would start at 0. It would have a constant slope, whose slope would be 9.8 meters per second squared, but negative because the line is sloping downward. Had you thrown the object upward, the velocity vectors would point upward, but then they eventually come to rest and it turns around. Notice that the acceleration is always g, even at the top where the object has come to rest. All right, so if we throw something and it does this, the acceleration is g at all of these points, even at the top, where our monkey hindbrain wants to say the object isn't moving, so it has no acceleration. And you really need to break that connection in your head. Things can be accelerated even if they are momentarily not moving. In fact, if they are to start moving, there must be an acceleration. So again, you can think of, if I have a thing at the top of the arc and I let it go, it's going to move downward. Right? It's going to do something like this, which means that there must be an acceleration there, causing it to go from being zero velocity to some non-zero velocity. So here we see the most expensive experiment ever in the history of introductory physics. This is taped on the moon during part of the Apollo 15 mission in, I believe, 1970, 70 or 71. It's probably worth knowing that the lunar lander was called the Falcon, and that will come up in an odd way in a bit. And basically, well, let's watch.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Now, of course, if Galileo had not been correct, then the last 4 centuries of physics knowledge would have been wrong. Everything based on it, which is Newton's laws and electrodynamics and everything that came out of it, would have been wrong, and they wouldn't have been standing on the moon. So this was maybe a little anticlimactic, but certainly interesting to see as for a certain value of real-world conditions that this actually does happen, that we didn't have to rig the hammer or feather or anything like that. All right. Notice that for objects in free fall on the same planet would have the same acceleration, which is g downward, but of course in reality air resistance is a factor in most cases, so they'll actually fall at different rates, and we'll talk about air resistance later in the class. We really can't do it as part of the kinematics chapter, but the dynamics chapter we can talk a little bit. But if we think that air resistance is not an issue, why not? Because we're talking about small distances and low velocities or objects that are streamlined. Bunch of reasons that let's say that air resistance is, if not zero, negligible. Under those circumstances, then all objects have the same free fall acceleration, even when they're moving up. And that, again, is just hard for some students to internalize, so I want to flag it for you, that no matter what direction the object is moving, its acceleration is downward. All right, so let's do sort of an example of that. There's a ball thrown upward, is thrown straight upward and falls back to the same height, and a student makes the graph to the right of the velocity of the ball as a function of time. So we want to know what, if anything, is wrong with the student's graph. If something is wrong, explain the error and how to correct it. If it's correct, explain how you know. So freeze the video, take a moment in your head, work out an argument, and then we'll go over it together. All right, this student's graph is incorrect. Because, well, why? Well, because the velocity of the ball, which is what they're talking about, we have to be careful here. This says that the ball is heading upward, which is fine, right? It has positive velocity, it's heading upward, but getting slower because that velocity is getting closer to the t-axis. That's all great. Hits this moment which is probably meant to be the moment of maximum height. And then it does this. I have to be careful because here we have the velocity, and it says the velocity is increasing. The object's getting faster. That sounds good. But the velocity is still positive. So if we were to draw this as a series of vectors, vector arrows, that'd be something which looks like this, and then gets a little smaller, comes to rest. That corresponds to this point, but then is upward and getting larger. So then a little bit, and a little bit more, and a little bit more, and like that. So our ball goes off to, as Buzz Lightyear might say, infinity and beyond. It doesn't come back down. It's slowed down, and now it just keeps going, and it gets ever faster and faster. What went wrong? Well, because the velocity should have, of course, the thing should have stopped, and the velocity should have reversed, and it should have come back down like that. How does that end up showing up on a velocity time graph? Well, the velocity should have become negative. So we should have seen a continuation of the original line and not this bit. Right? That's the error. And then we see that the slope of this line is continuous, and it would have the value of minus 9.8 meters per second square. Notice because the moment of the highest location is where it comes to rest, and that is an uninterpreted part. It hasn't changed. In fact, it's not distinct in any way for the shape of the line. There's no bend or change in the slope. So the slope here is also minus 9.8 meters per second square. Wow, that was pretty bad. Let's make that look a little nicer. At this location, the slope remains minus 9.8 meters per second squared, even though the velocity is 0. So keep that in mind. All right, the graph here shows the motion of a ball which is launched with a velocity of 14.7 meters per second upward, and which is moving under free fall. Note that it takes us exactly as long to fall from the maximum height, from here to here, as it took to reach it, from here to here. And that would be true anywhere. So we talk about being at what looks to be 5.5 meters. It takes as long to go from 5.5 meters to the greatest height as it does to go from that greatest height back to 5.5 meters. All right. What we say here is that there is a symmetry in the graph. This is a graph that can be divided, as shown here, along this point. This point in time is when it reaches its maximum height. It's the vertex of that parabola, and it splits into two identical parts that are reflected around that parabola. So we get that the time of flight is always twice times the maximum if you come back to where you started. All right, it's less obvious, but still true, that the speed of the downward portion is always the same as the speed at that height on the upward portion. So if we draw some tangent lines, and we say, well, on the way up, our tangent line looks something like that. On the way down, our tangent line looks something like that. They will have the same slope. They will make the same angle here if we talk about it at the same height. And that's a less obvious symmetry, but a true symmetry that we can also use, that it lands moving downward as fast as it launched going upward. Notice that at t equals 3 seconds, it hits the ball hits the floor again, and it's no longer in free fall. It's interacting with the floor. It's being affected by more than just gravity. It's not free fall anymore. The acceleration changes, and because of that, I didn't plot anything from here on out. I stopped doing it. All right. We can see the complete symmetry now. It's a flip about that axis of the velocity plot. So if I pick any time earlier, like 1.5 second, half a second earlier, or half a second later, they have the same velocity value. And we can see that the initial velocity and the landing velocity are opposite in sign, but otherwise equal. All right, this complete symmetry there. And then in a kind of weird way, even the acceleration plot, which of course is just minus 9.8 meters per second square, has a certain sort of degenerate symmetry of being just a line, and so has the same value no matter where you slice it. So it accidentally has that symmetry.